Fantastic. Okay,
Yeah.
mine's a little bit unconventional. I wouldn't say it's typical pro tip. All right. Oh, that didn't work. All right, can you see the presentation?
Wow. Yes.
Yeah, pretty neat, huh?
I would expect no less.
Well, good morning, ladies and gentlemen of the Intermountain Industrial Assessment Center, as well as Chris and friends. My name is Conrad Dewar, and today I'm going to be talking about an AR that I recently worked on. I think it's a super cool AR that hasn't gotten a lot of love in the previous years, which really is too bad because it can provide a ton of value if used in the right circumstances. So today I'm just going to be talking to you guys about what it is, when to use it, and just briefly how to find some savings for it. So to begin, I'm going to set the scene. How many of you guys have walked into a grocery store and you immediately feel this nice blast of air in your face? I see some people nodding. Okay. So it's actually created by this machine right here. And all it does is it brings in air from up here and shoots it out laminarly across the entrance like that. So why do people do this? Well, a couple reasons. First off, it's great at keeping things out. Particularly, it keeps out pollution, insects, dust, smells, keeps all of that from infiltrating the building. However, for our purposes, what we're most interested in is that it keeps conditioned air inside the building. So you can see over here in this diagram, here, let me get the laser pointer. You can see in this diagram, we have the nice cold air inside and the hot air outside. It's probably summer, maybe it's just Utah. And we don't want the hot air getting inside the building because then we have to recondition it and that wastes a ton of energy. So having this air curtain here is a great way to keep a barrier between these two sets of air while still allowing people and machinery to move in and out unhindered. This is great for things like loading docks, garage doors, or just any areas with a high temperature differential and frequent access. This is a really cool AR. It's only been recommended at the IAC 4 times in the last decade. However, it's been implemented 75% of the time. So I think it has a lot of potential.
Is that nationwide, Conrad, or specifically to the use recommendations?
This is specific to the University of Utah, which shows that potentially Utah customers have heightened interest. Good question. So it is at this point that I would like to mention that not all air curtains are the fan propelled ones like I've shown you. There are vinyl and PV strip curtains as well. And these are great for freezers, refrigerators, or rooms that don't get quite as much access. Ultimately, you do want to talk to the facility staff and see what they're most interested in, since they're the ones who ultimately have the choice of implementing this. But it is good to know that both options are there when you talk to them. So how do we find the savings? I'm just going to kind of briefly walk you guys through this and let you reference this presentation if you choose to do this. Ultimately, I got a lot of this from an IAC webinar courtesy of the University of Missouri. There's the YouTube link. I highly recommend you watch it. It's a great presentation. Ultimately, they got all of their information from the ASHRAE 2017 Fundamentals Handbook. Now, I have been searching high and low for this handbook, so I cannot personally verify that these equations came from the handbook, but I have seen this methodology on manufacturers' websites, so I know it's legitimate. So getting into it, it's just a simple mass flow problem where we have the energy is equal to mCp delta T, where the mass flow is just the air flow rate in cubic feet per minute moving through the doorway. And this can be broken down into the wind flow rate and the thermal flow rate. And the thermal flow rate is just a pressure differential created by differences in temperature. And then from there, once you know the energy, you can just use the difference in energy times the unit cost as your savings. So the main trick, as you might guess, is to find the wind and thermal forces. So the wind force is just the wind velocity times the area of the doorway times what is known as the effectiveness of the opening. Sorry. And you can see that for perpendicular winds that are going directly into the doorway, it's about 0.5 or 0.6. And then it's the smaller number for diagonal winds. And I will let you choose what number to use at your discretion. Thermal forces are a little bit complicated, but it's still not that bad. It's just a couple of numbers times the difference in temperature, times the area of the opening, times, and then under the square root, we have the gravitational constant G, the height of the doorway, and then the temperature differential divided by the inside temperature. Now, I do want to note that this is for heating. So if you were to do this for cooling, you would simply flip all of these temperatures. So this would be outside minus inside divided by outside. And there are units just for reference if you happen to use these same numbers. So once you have the flow rates, you just add them up and you can find the energy savings. Now, there's two things I want to quickly mention here. You will need to do this for every temperature, particularly because the thermal flow rate, as I just showed you, is dependent on the outside temperature. So Excel is a great tool. I highly recommend that you use it for these sort of equations. It's not that bad. I know a great group of crew like you can easily do it. The second thing I would like to mention is that you're going to have to do this calculation twice, once for heating and once for cooling, since those are separate calculations. So once we have the old energy, was there a comment?
Nope.
Whatever, Julie, sorry. So the old energy, once we have that, we just need to find the new flow rate. And that's pretty simple, actually. It's just the old flow rate times √2 over what is known as the center line velocity. And over here, you can see that for air curtains, we just use a value of 6. Next, you're going to multiply it by the square root of the door height divided by the width of the jet. Now, I do want to mention that the width of the jet is not necessarily the width of the doorway, so do be cautious when you're doing this calculation. And again, once you know the new flow rate, you just find the new energy and you can plug it back into the equation I showed you guys the first time. Hopefully this is just review for a lot of you guys. So for strip curtains, it's actually a little bit simpler to find the new flow rate. You just take the old flow rate and you multiply it by some reduction factor, which is anywhere from 0.2 to 0.1. And that's basically saying that roughly 10% or 20% of the air is going to be making it through this doorway that previously did. And then here's just the resource where I found that statistic. So there are a couple of things I want you to keep in mind. You have to include the electrical cost when using a jet flow air curtain. They get great savings, but they don't get it for free. Always use TMY data for the most accurate measurements and try to be conservative when estimating flow reduction for strip curtains. Now, this can be kind of tough, you know? How do we know that we sized it right? Are we using the right horsepower motor for the fan? Can we really be certain of the centerline velocity? I mean, are we sure that it's the same for every air curtain? And did we really do the reduction factor correctly? You know, there's a lot of variables that can give you wildly different saving estimate for these sort of problems. So now that you guys know the methodology, I'm simply going to direct you to these manufacturers. They all have saving calculators on their websites. So you can quite simplistically find savings estimates. For some of them, you will still need TMY data to supply them, but they know exactly the statistics of their air curtains and they'll be able to provide you some good estimates. I would like to mention that powered air curtains is probably the best one, simply because they're the only ones who are transparent on their savings methodology, and that aligns very well with what I provided here. But
yeah, that's huge.
Yeah, that was super nice. However, the IAC does have to remain impartial towards vendors. So if you do recommend one system, you're going to have to recommend, I would suggest, at least 2 more. So try to have multiple savings or multiple vendors listed. So for costing, these are some people that I've worked with in the past. They're happy to work with IAC students again. So if you're looking for cost estimates, unit and implementation, definitely hit them up. Last, we can move on to incentives. So you do get both gas and electrical savings for this sort of project, assuming that there's both heating and cooling. So for gas, if you're on a GS rate, you get $10 per decatherm saved per year, up to 50% of the project cost. Now, can anybody tell me how you calculate transport service savings or incentives?
Is
Maybe
this
one of
a
the new
trick
students?
question, Conrad?
Okay.
It's a really easy, it's a super easy answer. Just take a guess and you'll probably get it right.
It's a very easy cut. Chris got it. Yeah. Very easy calculation. There are no incentives for transport service, which is a shame, but it's okay because there is still the potential to receive Rocky Mountain Power incentives for the electrical savings. And because this is a custom project, you get 15 cents per kilowatt hour saved per year, up to 70% of the project cost. Now, there's some nuance here because these projects have the potential to cover 100% of the project cost. And I know that sounds totally crazy, and it is. So if you do work on this sort of project, I highly recommend you reach out to Chris. He's a Nextend consultant. He really likes working with the IAC. In fact, he's actually a former coworker of Michael. So he's totally happy to work with us and answer these questions. So if you do work on this sort of project and you do run into some crazy scenario like this, definitely talk to him. So I know I kind of breezed through this, but I had a great time going through this presentation. I hope you guys did too. Does anybody have any questions? Perhaps if we have time, Julie?
Sure. Nice job, Conrad. Did you just do this for the cannery by chance?
I did, in fact, yes. It was a fun project.
Anyone?
Seems like I must have killed it.
Okay. Yeah, nice job, Conrad. Thank you.
Yeah, thank you guys.
Realistically, just for context, that's not a ECM AR that I have necessarily pushed, but probably applicable to 70% or more of our assessments, and probably including the ones that we're about to do. So it's a good reminder, and you can hit up Conrad with questions if you want to propose any of those ideas for the next couple, or further out for that matter. Can I ask everybody, we got about half the group here that has their videos turned off. Can you all make a point to turn your videos back on? Thank you, thank you. Thank you, thank you. Quinn and Rashid and Parker, we're hoping you'll join us too with your video.
Yep.
So with that, pro tip, we're gonna transition now for the rest of the class time to talking about compressed air systems. And Chris Workman is here. He can tell you more about himself as he gets started with leading us through this week and next week. Before we hand it off to Chris, let's give him an idea of who is all here. I'm really sad that Sai is not here because she was the one I was going to specifically start our team introductions with, because Sai is the person who has expressed the most excitement about compressed air systems on our current team. Doggone it. So I guess with that, we'll just take it from the top. So Chris, this is our IAC current team. It is roughly a combination of 1/3 graduate students and 2/3 undergraduate students. The lone business student will be our first introduction, so we can give her a highlight for today, but otherwise everybody else is engineering students, either mechanical or chemi, just FYI. So here we go. Ready? Popcorn introductions, and you get to start it from there.
I'll take that as my cue. So as Julie mentioned, my name is Anne and I'm the sole business student. I came to the U from a background in the energy industry, working for a utility grid scale project developer asset manager, and excited to be a part of the team. I will popcorn to Blake.
Chris, I'm Blake Billings. I'm the lead graduate student here at the IAC. Been here for coming up on 2 years, so happy to be here. I'm gonna call on Jake.
Hi, I'm Jake Immonen. I am a first year PhD student working for Dr. Powell. And so this is also my first year in the IAC. And before that, I did some water treatment engineering work before becoming a PhD student. All popcorn, Mateo.
Hi, my name is Mateo Ismales. I'm a fourth year mechanical engineering student. I am also an international student from Peru. And I've been with the IAC for about a year now. I'll popcorn it to Conrad.
Hi, Chris. I briefly introduced myself. My name is Conrad. I've been with the IAC for about a year and a half now. I'm a third year chemical engineering student. And quick little fun fact for you guys, a Nook, the Amazon books, have a one that's full of books that has a bunch of books downloaded actually weighs more than one that doesn't have any books downloaded. I'll let you think about that. Maybe tell you why later. Let's go Popcorn Brooke.
I'm Brooke Yardley. I'm a third year chemical engineering student.
Brooke has apparently gotten started with her weekend early.
And fun fact is I have a mountain goat on my hat, and I'll pass it to Yunji.
Yeah.
Almost.
Okay. Hi, Chris. My name is Yunji Chen, and I'm an international student from China. And I'm a first year PhD student in chemical engineering, and I also work for Dr. Powell. And this is my first semester in IAC. So I will popcorn to James.
Hello, everyone. I'm James. I've been with the IAC for 3.5 years or something now. Can't find a reason.
Amazing.
I love it. But yeah, I'm a senior in mechanical engineering graduating this semester, so looking forward to that. I'll popcorn Jace.
Chris, I'm Jace. I'm one of the new members to the IAC. Started in January, so I'm enjoying it so far and looking forward to learning more. I will popcorn to Abby.
Hi, I'm Abby. I am a chemical engineering student, started in the IAC at the beginning of this year. Fun fact, I was looking into my ancestry the other day and I found out I have a great grandfather who was like into math and chemistry, and so was basically a chemical engineer before chemical engineers were a thing. So that was really cool. And I will pass it off to Michael. You haven't gone yet?
No, I am Michael Reynolds. I am a graduate student. This is my second semester in a PhD program. Before coming here, I worked in energy efficiency for Nexent. So I'm pretty good friends with Chris Engeweirden that Conrad referred to earlier. I will popcorn it to Sammy Partridge.
Hi, I'm Sammy Partridge. I have been a member of the IAC for a few weeks now. I'm a sophomore chemical engineering student at the U. And that's probably it for me. I'll popcorn Parker.
I am Parker Bodley. I am also a second year chemical engineering here at the U. I'm one of the new hires. I guess a quick fun fact about me is that I have a pet turtle named Cookie. So there you go. And popcorn Quinn.
I'm Quinn. I am in my last semester in the mechanical engineering program. I've been with the IAC for like a year and a half now, I think. Fun fact is Johannes Kepler, like the guy that did Kepler's laws of planetary motion. It's like one of my great uncles. So that's kind of cool.
Wow.
Let's see, who else have we not popcorned? Rashid. Let's do Rashid.
Hi, Chris. I'm Rashid. originally from Nigeria. I've been in the United States for about 7 years now. I'm a junior in mechanical engineering, and I've been with the IAC since January. And the fun fact about me that everybody already knows by now is that I love basketball. And I think, is that it? Nestor.
Yeah, my name is Nestor. I'm a fourth year in the mechanical engineering program. I've been with IC for about a year and a half. Fun fact about me, Julie and Abby and I were actually just talking about languages that we speak, and I'm actually semi-fluent in French. And I will pass it on to Lizzie.
Semi-fluent? Wait, Nestor, can you tell a joke or something?
I said semi-fluent. I don't know any French jokes. I'll come up with one next time.
Okay.
Hi, I'm Lizzie. I've been working with the IAC for about 3 months now, and I am a first-year chemical engineering student. And I will popcorn Andrew.
I'm Andrew Meldrum. I'm a third-year chemical engineering student, and I've been with the IAC for almost 2 years now. And I guess fun fact about me is that I am like almost trilingual, getting there, not quite yet, but. And where's the list of people? Sorry, my phone is up.
I think that might be everybody, Andrews. Can you raise your hand if you have not introduced yourself? Yep, I think we're good. So thank you, Andrew. Thank you, everybody. If you all haven't heard me say this, compressed air, and if you haven't experienced it yourself, compressed air is one of the sort of staple fundamentals of the IAC program for any assessment that we do. So I'm really excited and super grateful that Chris Workman is here to join us today and next week to focus in on that topic. Chris, with that introduction, I will let you take it from there to tell everybody about your experiences with compressed air systems and so forth. Sound good?
Cool. Sounds great. Thanks, Julie. Nice to meet all of you. So let's see. Let me share my screen real quick. Can you guys see that?
Yeah, looks great.
Okay, cool. So as y'all know, we're going to be talking about compressed air systems today. I'm Chris, and get it to go here. Here's just a high-level outline about what I was planning on covering with you guys. And maybe before we dive into this, I'll just mention that I intentionally didn't get too quantitative on it today, because I think that there's enough with compressed air to just, I think some of the hardest things to understand for me when I first got into it was just how the pieces come together. What are some of the different types of equipment, because they're not all the same and they all serve different purposes. And yeah, how kind of the measures, the equipment, the systems sort of all work together. And give you kind of an understanding of that. So here's an outline. We're going to talk about what it's used for, why it's used, kind of why we manage it, then dive into some of the pieces of equipment, talk about some of the controls that drive some of that performance, talk about set points, what you might see, what you keep an eye out for, get into measures, and then talk about questions and talk about some assignments that I've doled out for each one of these small groups.
Chris, really quick, can you go back to your first slide just really quick? I want to make sure, Michael, are we recording? I don't see the normal indicator that I see.
It is recording.
Okay, great. Thank you.
Cool. Yeah, no worries. So quick background on me. I have a bachelor's and master's in mechanical engineering. The did undergrad at UC Berkeley and actually met Dr. Udell, if any of you know Dr. Udell, and followed him out to Utah in 2008 to do my master's at the U. You know, didn't think I'd end up sticking around in Utah for now 13 years, but love it here. It's definitely home. Like professional credentials, mine are very similar to Julie's. Have a PE and a CEM. And I've been doing this for about 10 years when I finished my master's degree at the U. You know, I've been a project consultant, I've been an energy manager for Intermountain Healthcare for about 5 years. On the owner's side of making energy related decisions and running plants. I've been a utility program administrator for a third party program administrator, like similar to how Nexent is. And
Yes,
now my current role is, oh yeah, Joe.
I was just going to chime in. We work with folks like Cascade and KW in that Rocky Mountain Power role regularly. So Chris was basically one of those folks, guys.
Yeah, exactly. And now I've just recently pivoted. So at the same company that I was doing the program administration for, called Willdan, but I'm now in an arm of the group that does turnkey or design build project delivery. Let's see. So we'll start with some of the basics. You know, everyone's somewhat familiar with compressed air, everything from air in a can you might use to dust off a keyboard to something that is, you know, air compressor you have in your garage. But what is it used for in industry? And this is by no means comprehensive, but these were some of the things that were top of mind when I was thinking about this. Actuation and control is a big one. So that could be control in a commercial building, even if you have a really old control system that doesn't have electronic actuators to move parts for dampers and actuators and things like that on dampers or valves. Those might be mechanically actuated by compressed air that's giving them the oomph. Up here is a pneumatic actuator. Could also be used for material conveyance. So, for example, worked in a site in Wyoming that was making baking soda, and they use compressed air to move the baking soda, the raw materials, like through a pipe across the plant from one side to the other. Could be used for scrap removal or blow off, that when you're maybe cutting something out, there's excess material on the sides and edges that falls away, and that they're using compressed air to kind of blow that and kind of keep the work area clean. Could be used for mixing, aerating. Done work at wastewater treatment plants and below the tanks for settling and things like that, or other chemical processes. It worked at Kennecott too, and they use compressed air under a lot of the tanks. It inject it into the fluid, and it would kind of circulate it when you introduce air at 100, 150 psi. It circulates the fluid. Some of the really kind of top of mind things, just for maintenance, for tools and cleaning, same concept as air in a can. And then probably the nasty one, we'll talk about this in recommended measures, is spot cooling, which is almost always an inappropriate use of compressed air, but you still see it a lot. Next one of why do people use compressed air for these purposes? And I say that because you could accomplish a lot of these jobs in other ways. So let's talk about kind of why, so that when you're talking to plant staff, you can understand a bit of where they're coming from. And the first one is ease. So if there's already compressed air piping running around a plant, and infrastructure there for someone to tie into, and they have a problem, they have a cooling problem, they have a cleaning problem. It is unfortunately a quick and dirty way to like address and solve that problem. You know, even if you have something that you could set up a little motor driven system like a fan or a circulation pump, compressed air is very forgiving in terms of designing that. A lot of times there's a lot of solutions that you can accomplish with compressed air, just piping into the source, having a ball valve, and kind of modulating that ball valve to get the volume of air that you want until the job's done. That said, it's a low first cost, low barrier to entry, very easy, but it's a huge life cycle cost from energy. The next one, which is really valid and important, is like fire and explosion risk. So if there's some sort of elevated arc flash, like arc blast, explosive dust concern, compressed air is a great application and a really applicable application for any in place of something that's like a motor driven system, because motors do have a spark or explosion risk. If you're in, like, you know, parts of a refinery that's a concern, or in mining or any sort of dusty environment where there might be particles floating around that you know, can catch fire. Third one is cleanliness. This one kind of goes without, I don't want to say goes without saying, but you got to think about other ways a lot of these problems could be accomplished. If you're trying to like drive something and use fluid power for like a pumping or a steam, and use another fluid like a liquid or steam, and there's a leak, it makes a big mess. So compressed air, the leaks, you know, no one's really going to, it's not going to cause a huge emergency. It's just going to waste a lot of energy. And then the last one is process equipment driven specification. And so what I mean by this is usually a lot of you that have been doing this probably start to see that you can think of most manufacturing plants kind of as the process equipment that's really touching the product that that plant is there to make, whether it's baking soda or window frames or machine shop. Like, there's equipment that's actually touching the process. And then there's all the utilities that serve that equipment and the overall building. So the utilities, you know, compressed air, steam, heating water, things like that. So the process driven equipment, those manufacturers often kind of, it's sort of a take it or leave it on what sort of utilities they want you to hook up to drive the equipment that they've designed. So sometimes you're just locked into it. And you know, why do we manage compressed air? You guys, I'm sure, have come to realize this. The first one is, you know, cash money. It costs a lot of money to drive compressed air systems. It's one of the most expensive utilities in any sort of industrial facility, and there's a few different reasons for that, and they're also tied together with the environmental impact. Compressed air is expensive because it uses a lot of energy, which therefore has a very large environmental impact, right? Because all of our electricity generation current state has a significant environmental impact. So those two things are tied together mainly because air compression ends up being about 90% heat. Like, air compressors are okay at making compressed air. They're great at making heat. Heat is their number one byproduct, unfortunately. So I've kind of added a couple of schematics here that you can see. So if you have your work into the compressor via the main drive motor, about 90% of that ends up being rejected via air directly at the compressor or to some sort of maybe water cooling loop to another load or cooling tower. But either way, about 90% is a good rule of thumb, you know, of energy, electrical energy you put in, you're not getting out in fluid power of the system. It's just going to heat. And then maintenance of the or performance of the overall system. A lot of times, because compressed air is kind of hidden, I'd say, like pushed back in a machine room, a lot of people don't understand the equipment. When there's leaks, when there's problems, like compressed air is invisible, so it doesn't catch people's attention quite as much as you know, steam systems, like hydronic systems, things like that. So what that ends up doing is it can cause system degradation issues and impact the process in ways that like happen so slowly that a lot of times the plant staff don't realize, but then when you fix them, it's a huge bump in how well the process works when you fix it. So now this is kind of the meat and potatoes of the presentation. And I'm an equipment nerd, so this is sort of what gets me excited, is talking about some of the source equipment. So the equipment back at the compressor room. So a quick overview in this schematic here is that we have our air compressor, this shown here by the beige box. We have air dryer, which is this kind of gray with the red little control unit on the end of it. In the schematic, we have a couple different filters. We have like a mist eliminator, or they're calling it a coalescing filter. It's kind of the same difference between the air compressor and the dryer. There's a dust filter downstream of the dryer. And then there's some storage, or also called receivers, air receivers, in a couple locations. You know, one here, call this wet storage. We'll talk a little bit more about that, between the compressor and the dryer, and then a dry receiver kind of after the source equipment, just sort of as a buffer as you go out to the system here. So let's drill a little bit more in. So there's a lot of different types of air compressors, and kind of shown two different, one list, and then this sort of tree graphic here that I pulled off the internet. But I want to kind of underscore that by no means are either one of these comprehensive. So I was talking to Julie about, I want you guys to leave this with kind of understanding like what in my mind you're going to run into most of the time and what you can effectively change the most. Because not all these compressors can you do as much with in terms of energy efficiency measures. So first, let's kind of talk a little bit higher level category. So we have positive displacement compressors and dynamic compressors. So positive displacement compressors increase the pressure of the air leaving the compressor by reducing its volume. So the easiest one to think about this is a reciprocating compressor, which is like, really think of it like a piston in a car. Moves up and down, and valves open and close so that it compresses the air as the piston moves up in its stroke. You then have, it's a little bit harder to think about conceptually, but a rotary screw compressor. And if any of you are kind of car buffs, it's no different than like a top mounted supercharger on kind of like your old muscle car, where you have screws, there's a male and female, and they kind of intertwine. There's actually a constant volume that it's continuously pushing from its suction to its discharge in that screw along its length. And then within the screw we're going to spend a bit more time going into. There's oil flooded screws and oil free screws. So oil flooded screws, jump ahead here. Oil flooded screws this is a screw compressor here. This is the actual compressor, the air end piece of it itself, have oil injected into this casing here, in with the air and the oil go into the compressor itself and enter those screws. Whereas an oil-free compressor does not have any oil directly in contact with the screws and the air. There is oil to lubricate bearings and gears, but there's never any direct contact between the air and the oil in an oil-free. So that's important to understand because it impacts some of the part load control that you can do. Oil flooded to air-free, or sorry, oil-free. Oil-free has some more restrictions. But let me get back over to here. But I have oil flooded screw as kind of highlighted here in red. The reason being because that is going to be like 90 to 95% of what you're going to see in industrial applications. They could be anywhere from 25 horsepower oil flooded screws that are serving end uses in a small machine specialty machine shop you guys go into, all the way up to 250 plus horsepower oil flooded screws serving like large manufacturing facilities.
Chris, I don't want to steal your thunder, but do you have any quick tips for the group of how to identify the oil flooded versus oil free?
Pretty much just nameplate information is probably the quickest way, I have to say. Yeah, once you'll start to see sometimes it says on the side, like quite frankly on the package as part of the branding, oil free. Usually you can usually assume if it doesn't say oil free somewhere that it typically is oil flooded as well too, and they're just so much more common. It's probably like a 9-to-1 ratio that I see out in the field. And then kind of go to dynamic compressors, which are compressors which transfer energy from a rotating impeller to the air, and then that impeller imparts velocity pressure, which is then converted to static pressure, like through a nozzle to discharge to generate, the leaving discharge pressure that you want from the compressor. So centrifugal compressors, another disclaimer, centrifugal compressors are definitely a very large industrial component, but they're not nearly as common as oil flooded screws because they're much bigger. You need to be at pretty large size systems usually to see those. So yeah, I'd be surprised if you guys see those in the IAC. I quite frankly haven't done a lot of projects on them because they're not as common, but they're out there. Then want to talk about air dryers. So air dryers are an important part of the compressed air system. And the reason being is that when you compress air from atmospheric pressure up to operating pressures of 100 and 125 psi, the air is fully saturated when it leaves the compressor. So it's very wet, we like to say. And so you don't want to just send that wet air out to your process or out to the system because it's going to wreak havoc on piping and eat it away. It's going to cause a bunch of your equipment to not actuate because it's not designed to handle water and condensation in it. So we want to knock all that water out before we send it out of the compressor room, ideally. So there's two different types of dryers that we do this with. First one is called a refrigerated dryer, and it's this guy up here that looks kind of like a gray and yellow box, the one I have on the slide. And refrigerated dryers have a small little refrigeration circuit in them. They have a condenser to reject heat to the space that they're in. They're usually air cooled. They have a little refrigeration compressor, and they have an evaporator, which is a heat exchanger between the refrigerant and the compressed air. So they're trying to drop the temperature of the compressed air in order to pull the moisture out of it, like a cold Coke can on a humid day outside. So there's two different types of refrigerated dryers. They both look nearly identical from the outside, like this box here. But there's cycling and non-cycling. Non-cycling are not as efficient, whereas cycling are more the energy efficient type. And the reason being is that cycling dryers can turn off the compressor when their demand falls. They're much more insulated around that heat exchanger and the evaporator. And they have much more of a thermal mass inside that insulated piece. So they'll run to a certain set point and then turn off if demand is low on them and kill that compressor if they don't need the cooling. Whereas a cycling dryer, if it's regardless of demands, that refrigeration compressor is running the same load. So there's no turn down to track your compressed air demand. Whereas there's a relationship between the mass of air running through a cycling dryer and the amount that the refrigeration compressor is running if it's a cycling version. The other type is desk-and dryers. So desk-and dryers, there's about 4 primary kinds. There's heatless desk-and dryer. So that purely just uses a deskant like, silica beads. And it uses, you can see in this photo here, the one in the bottom corner, that's a deskant dryer. They're almost all have 2 towers. And the reason being is that this deskant has to be regenerated. What I mean by that is the operating mode of these is one tower is always online. So the compressed air that's going out to the system, going out to loads, is always flowing through one tower and then out. Whereas the other tower is getting regenerated when it's offline and not the one serving the loads. So what happens to regenerate the offline tower is that a little bit in a heatless deskant dryer is that a little bit of compressed air is bled from the incoming stream to just flow through the offline tower and then out the atmosphere. And that expansion dries out the deskant and kind of regenerates it and dehydrates it. But you're still paying to make that compressed air back at the compressor motor, and then just exhausting it to atmosphere. But it's kind of what you have to do to regenerate the tower. And then those towers switch. We'll talk about that switching here in a minute. Heated deskant dryer is that you're still bleeding off air from the incoming compressed air stream to run through and regenerate the towers, but you're heating it before it goes into the regen tower, and that just kind of gives it a little extra oomph and decreases the volume of compressed air that you need in order to regenerate the tower. heated blower purge, you don't use the incoming compressed air to regenerate your offline tower. It's still same deskant kind of chemical process, but you are using ambient air that's in the mechanical room to suck into a small fan and then heat that air and then run it through the offline tower and then exhaust it to atmosphere. So you're then not paying for that compressor, that regen back at the air compressor. You're paying for it locally at the dryer with this fan and the heater energy. And the fourth kind is, I've actually never seen one on a project, but I'd be really excited to do some sort of retrofit because they're really cool. And that's heat compression. And I think they're really cool because they take that 90% wasted heat from the compression process at the compressor itself, and then use that heat at the dryer to dry out your air. So there's like a lot of pros and cons to get into designing that, but it's, you know, from an overall system perspective, makes a whole lot of sense that you're not just throwing that energy away and using a different energy stream at the dryer. Another thing, I want to talk about dew point demand controls for a minute and kind of what the differences between these two dryers are in terms of dew point. So the dew point of the leaving air from a refrigerated dryer is much higher than a deskant dryer. So usually a set point on a refrigerated dryer is about 40 degrees Fahrenheit, whereas a deskant dryer set point is often like negative 40 degrees Fahrenheit. And so that's kind of gets into applications which we'll talk about in a minute. But I want to mention the dew point piece of it as well in terms of controls, because on the deskant dryers, within each one of these types of, or the first three, the switch between the offline to the online tower to the offline or regenning tower can be handled two different ways. It can be handled based purely on a timer that's set based on worst case scenario of how long can I stay on my online tower and push this wet, saturated, compressed air through it before the media is totally wet and I have to switch over to my regen tower, versus actually having controls that look at what that discharge dew point is from the online tower. So the benefit of this is if you're not running your dryer, which most compressed air systems aren't running at full capacity, if you're not running the dryer at full capacity, that when you switch the towers prematurely, like in a time setting, you are going to be exhausting more of that compressed air and regenerating it unnecessarily because it's purely just based on time. And you're going to be just sending that compressed air from the source out to exhaust in the regen cycle. So we mentioned this a little bit, touch on a little bit more, types of storage. So compressed air systems, so the wet compressed air is before it hits the dryer or is run through the dryer. So we have wet storage usually, which is like an air receiver that is somewhere between the compressor discharge and the dryer itself. That's shown here with the blue box. We'll talk about condensate in a minute, but that is condensate management at the wet receiver is really important. And then there's dry storage. So that's any sort of storage. It could be right at the compressor room or it could be out in the system by the loads. But any storage that is downstream of your air dryer. Now condensate. So condensate can fall out in a number of places in the system. We're trying to catch it and not have any of it really downstream of the dryer. So most of it is in the compressor room here. But you get condensate even upstream of the dryer. Let's say I mentioned this wet compressor. If you have saturated air that's hot and under pressure at a high velocity leaving this pipe out of the compressor discharge and then going into the wet receiver, as it goes into the wet receiver, it expands and slows down. So if there's entrained droplets, they're going to fall out to the bottom of that air receiver, and they're probably just going to cool down as well too. So you're going to get some condensation. So that matters because you're going to get water puddling up in the bottom of your receiver if you were to do nothing. So you got to get that water out of there. Really
Team,
old school would have. Yeah,
just to chime in really quick, Chris, I was going to point out, we often talk about zero loss drains. So this is exactly what we're talking about when those conversations are happening.
Yeah,
this is a
exactly.
routine opportunity.
It is. It's a good one. So like, there's actually another way to manage condensate drains, which is even worse that I didn't list here, and that's just leaving a valve cracked. Like sometimes the worst way to do this is if at the bottom of the receiver they had some sort of valve and they just left it slightly cracked, so it's always bleeding a bit of air, condensate, and also air out of the bottom. You know, you're just throwing away compressed air if you do that. But you know, I've seen it. The next kind of middle ground way, but there's still room to improve on, are timed drains. Time drains, that's what I have here on the left-hand side. It's got this little table on it and the cord. So time drains do exactly what they say. You set how frequently the drain opens. So every 5 minutes, every half hour, something like that. And then you also set the duration that the drain is open when it does hit that frequency. So, you know, whether it's open for 2 seconds, 5 seconds, 10 seconds, something like that. And it's adjustable. But that doesn't, the valve is going to open whether there's condensate there that needs to be drained or not. And you're usually going to set that time drain as a worst case scenario for the wettest, like highest condensate demand system, just to cover your butt. So what that means is that a big portion of the time you are wasting compressed air because that valve opens, there's no condensate behind it, and you're just venting compressed air. So the solution that sounds like you guys have talked about are zero loss drains or no air loss drains. And that's kind of this one right here. And there's, I believe that they kind of do this two different ways, how those work. Some of them, I think, just use like a simple float, like, you know, in a toilet or something like that, where there's a float that rides on the liquid and opens the valve, the float rises. The other way is I think that there's like probes that sense conductivity. If these probes, it completes the circuit. I think that that's how it opens the drain. So if there's no liquid in there to complete the circuit between these probes, it doesn't open.
Mateo, go ahead and chime in with your question.
Sorry, yeah, I was going to ask if instead of only time drains, if there are drains that use a sensor so that like the water reaches the level, it starts draining it.
Yeah, so that's pretty much exactly these zero loss or no loss drains. Yeah, yeah. That they'll only open when they sense condensate in them. Yeah. So these ones actually, that's kind of why the scale doesn't show up in this picture very well. But this time drain is very small because it's really just a valve, and that's almost like the size of a little like AC adapter you put on the wall. Whereas this no loss air drain here is much bigger because it actually has a reservoir that accumulates the condensate because you need some sort of volume for it to then sense with the probes or with the float that, oh, I'm at my limit, I need to open and let that out. Whereas there's no capacitance in the time drains. They're just a valve.
Is there some sort of maintenance difficulty costs associated with the no loss drains that's not with the other ones?
So my gut is that there's kind of there's two reasons driving why the no loss or zero loss drains are not immediately implemented and not the standard. The first one is first cost. They cost a bit more. You know, they're a bigger component. There's more raw materials, but also that they have a little bit more sophisticated controls. And because they're not just purely like a very basic timer. But the second reason is that, you know, a lot of times it is like slightly more complex. It might kind of seem crazy to even see a difference here, but it's slightly more complex to have something that's responding to load in this way versus just like a dumb timer. So that means it has a tendency to break and, you know, be a little bit more expensive to fix and more difficult to troubleshoot potentially.
Hey, Chris, I got a quick question.
Yeah.
Just a real-time question from an assessment that would be interesting to explore with you just for a couple minutes. We have a current system that we are doing an assessment on where they basically have purchased a dryer. They have like a 1250 horsepower compressor, and they have purchased a dryer, but they have not made it a priority to install the dryer. So it is literally sitting in their compressed air room on the skid. And you might just use that as a teaching opportunity for a second.
Sure. So maybe do they not have a dryer at all in the system, or like it's failed?
Right now they literally have no dryer in the system because they've purchased it but not installed it.
Gotcha. My hunch would be like it's probably actually not a whole lot of. First thing is I would tell them like you're destroying your piping system and all your process equipment, like causing tons of undue harm, like totally separate from energy cost savings. We've got to help you with that. But then the second one is the maintenance staff probably have opened up a bunch of valves and have a whole bunch of bleeders all over the place, I bet, because they probably do get condensate accumulating. And so that wasted compressed air does show up back at the compressor in terms of excess energy usage because they're just venting it. So I don't know, that would kind of be my 2 points to try to bring up with them and push them on.
Yep. Thank you.
Does that help?
Yes.
Yeah,
I just was reminded of that and wanted to use it as a real-time application of this conversation. Thank you.
Yeah, no problem. Let's see. So now kind of want to drill a little bit more into the compressor packages and talk about compressor controls. And maybe now just looking at this, probably should take a step back and say, by compressor controls, I'm referring to compressor capacity controls. So, you know, the capacity of air that the compressor puts out is not always going to be 100% equal to what the load is demanding of the system. You know, the compressor full package or multiple packages together is probably more than what the system needs. That's how you designed it. So you have more there in case you need it. So how are we going to tell that compressor to reduce the amount of air it puts out so you don't overpressurize the system and make things blow up? Well, that's the compressor controls that do that. So reciprocating compressors, not that there's huge savings here, because usually we don't see very large reciprocating compressors in industry. But I'm going to start here because it's the most accessible to, I feel like, what we see kind of might see it at home or growing up. And so a reciprocating compressor like you'd have in your garage is just start-stop. It has a high pressure set point and a low pressure set point. And when the pressure in the system falls to a low pressure, let's say 90 PSI, starts the motor, the compressor starts moving. And then when it hits a higher pressure set point, call it 100 PSI, whatever you set it at, compressor motor turns off and it stops pumping. And then it just kind of seesaws between those two. That's capacity controls. On but then on oil flooded screws, there's quite a few more. And on this diagram here, this is a screw compressor, a package. I've highlighted in red the inlet valve, because that's what governs and kind of drives a lot of these controls, is this inlet valve. The inlet valve is usually just like a butterfly valve. Again, for anyone who's sort of like an automotive geek, the butterfly valve is almost like the throttle body on a car. And so it can modulate in inlet modulation, so like infinite points of adjustability from being totally closed, if this is the inlet pipe, totally closed like a plate, to modulating partially open. So it turns like that in the incoming airstream. So inlet modulation is one means of control. Load unload also uses that inlet valve, but it only has two positions: wide open like this, making air, or fully shut. It's either making full compressor capacity or no air at all. That's load unload. Slide valve is a bit more complex to show. It does not involve the inlet valve. The inlet valve is fully open, but what it does is actually changing the displacement of the screws. The mechanical means that shortens the length of the screws, so it's effectively decreasing the displacement of the compressor. Then the next one is VFD. You guys are probably familiar with VFDs, where you're then just slowing down the speed of the motor, so reducing the rotational speed. Whereas these first three, inlet valve, load, unload, slide valve, they're all constant speed operations. So the motor is still turning at the same speed. You're just changing it on the mechanical end. And then the last one is a shutdown or start-stop timer. This can be applied, a shutdown or start-stop timer could be applied to many of these modes here. But you know, there's I guess a few things maybe to be aware of. Primarily that when you get into motors over about like 10 to 20 horsepower, that they have a maximum number of starts you can have during a given hour, where you can overheat the motor and melt the windings, because there's inrush current every time you start it. So that's high level. So to go back through this, inlet modulation is your least efficient means of control. It's at zero flow, only about 68% efficient. Whereas load unload at zero flow is anywhere from 20 to 30% efficient. And slide valve. These are kind of aligned in increasing improvement in capacity, whereas the VFD has nearly an ideal part load performance curve between the power required and the flow delivered. So again, I mentioned didn't cover centrifugal compressor controls and didn't cover too much on oil-free screws. The reason being, like, oil-blooded screws are going to be 90%, 95% of what you're probably encountering out there in the field.
Chris, time flies when you're having fun.
Yeah.
We probably have about 5 minutes left for today.
Okay.
I can help you manage that offline, but I just, for now, some students may be able to stay. Some also may have classes that they have to move on to. So I wanted to give you a heads up.
Cool. I have a handout with that I'll send to you guys to distribute with the assignments. So,
okay.
But yeah. Common set points: compressor discharge pressure, you're often going to see between 80 and 120 psi. I recommend trying to keep that under 100 psi. Just because the compressor can make a higher pressure doesn't mean you need to deliver that. And you also need to keep into account some of these means of control, like load unload or start stop, have a high and a low limit. There's a dead band there, so it's not just like a single point necessarily. Dryer dew points, refrigerator dryers, it's like I mentioned before, usually about 40 degrees Fahrenheit, deskant, -40, but those can be adjusted. You know, if you can move those up, it saves energy. And the deskant one is driven by process needs and ambient condition, and is often driven by ambient conditions, particularly a lot in like Wyoming and Utah. And so you can turn that temperature up during the summer, for example, when it's not cold. And you don't have a concern of condensation. Here's some low-cost energy efficiency measures. I think you guys are aware of a lot of these. Pressure reduction, so reducing the pressure at the compressor, increasing the dew point at the dryer, turning off the system during non-production times. You know, that's even during lunch, like at some places would make sense if it's a small operation, if they all break for lunch at the same time at like a machine shop. Adjust shutdown timers. I've seen a lot of screw compressors that they sit unloaded and the shutdown timer is not enabled, and it never shuts down after like a half hour, an hour. Next one, leak audit and repair. I know that you guys are all over that. The big thing to be aware of there is people often want to focus on the big pipe, like the main runs and headers overhead, things like that. That's not where you're going to find the leaks. You're going to find the leaks at the equipment, because that's where the vibration and the disruption from operators and people walking by it and breaking stuff is. It's not going to be up in the pipe rack. Next one is just to repair anything that's broken. And again, seems obvious, but like these are all mechanical systems. If it moves, it breaks. And when it's broken, it's not going to operate as efficiently. It was there in the first place for a purpose. Retrofit or capital measures, as we typically call them. Converting a compressor that's currently running modulating to load unload. So instead of that inlet valve kind of modulating, just having it run two fixed positions, this becomes capital because you often have to add additional storage to the system to accommodate that. Installing a sequencer or implementing cascading pressure controls. So instead of having multiple compressors running in parallel, like just have, you know, one running all out rather than two running 50% capacity, have one running all out. That will improve part load performance. Adding system storage sometimes, if it's grossly inadequate, even if you don't change the controls, can help. adding dew point demand controls on desiccant dryers, replacing a constancy compressor, particularly if the compressor is at end of useful life and it's failed. You really want to look at replacing it with the one with the VFD in a lot of cases. And then converting inappropriate end uses to to something that's not compressed air, like maybe a low pressure blower. So that kind of sums it up, folks. I have some assignments for the small group, and maybe should I open it to questions, Julie, or quickly give people a heads up on the assignments piece?
Let's talk about the assignments. I think, Chris, it would be good next week to allow a little bit of time. I know there's all kinds of questions that people have, and we've touched on a lot of topics here that people like to talk about. So let's allow for that, a good amount of that next week. And for now, let's go. So everybody knows that there is LLC work to be done between now and next week. Let's go into that.
Okay, cool. So I'll forward this on to Julie and Michael, and you guys can get this out to the class.
Yeah, great.
It's my contact info and outline, and here are the assignments on the third page here. So I've broken them out by the different groups, and kind of see 3 groups are doing data analysis on 3 different data sets that Julie, that you said that they have access to, from the automotive equipment to the insulation to the feed milling. Trying to do some plots and sort of figure out what's going on with the local operation of the compressor. And then group 1 and 5, experience and QRS, are filling in some more color on what I went through today. Like, what's the range of equipment sizes? Like, trying to put some numbers to these part load performances. And then for QRS, looking a bit into power factor and like conversions between ACFM and SCFM and some other units that are specific usually to compressed air systems and why they matter.
Okay, and it looks like you have some resources there that people can use for this.
Yep. Yeah. So these are just equipment manufacturer sites, but those should really help out groups, particularly group 1, but also, all the groups that encourage you to go click around, look at equipment type sheets, because you can learn a lot. Look at KG data sheets.
So group, team, class, we are purposely not using our customer names here just for confidentiality. But the beautiful thing about this timing is that basically with this approach, the teams that just got data for compressed air systems can leverage this assignment to help them advance the ARs associated with those particular assessments. And then we have the other automotive safety equipment data set here that we just finished up on. And generally speaking, I try to align as best as possible the people that are working on those assessments with the people that are in these various groups. Hopefully this turns out to be a win-win for you guys in a couple directions.
Okay.
We'll get this
for next week.
Oh. Yes, go ahead, Chris.
So for next week, Julie, I was just based on our conversation, set this up as the assignments were basically for each one of the groups to present on these things next week. Does that sound like a plan?
Sounds great. So we'll say 10 minutes or so for each.
Sounds
roughly.
good.
Similar to what you guys have done, what the class has done for previous assignments. Just keep in mind that the ask here is 2 hours per person per group, and do what you can with that amount of time and prepare a presentation in that 10-minute range. The good thing is really stick with that 10-minute range, because you're going to have the opportunity to present this while Chris is engaged with our class, and there will be some discussion that will likely be generated from that. So keep that in mind as you're presenting. We want to sort of be crisp with our presentations and succinct so that we have a little time for discussion. Okay, Chris, any compressed air jokes to end out today? The Dilbert one was pretty good.
I'm not going to put you guys through that, but yeah, appreciate the opportunity. Yeah.
Thank you very much. Thank you, Chris.
Yeah.
Thanks, class.
Cool.
Thanks, team.
Thanks,
We'll be in touch.
Yeah.
Bye-bye.
Thanks, everyone. Take care. Bye-bye.